Welcome to this very video. If you've been following us, we've done introduction to organic chemistry. We've done characteristic features of organic compounds. We've treated tetravalency of carbon. We've treated catenation. So in this video, we will be dealing with homologous series. So permits me to go down. So if you have not subscribed to my YouTube channel, what are you still waiting for? I actually want you to go down there, hit the subscription button. This will motivate me to make more videos and more classes. Don't forget to like this video and share. So let's start. Let's just get started. So if you look at before I go to the explanation of the definition or whatsoever, let me explain what homologous series is. Now, think of it this way: we have more than 1,000 organic compounds, thousands and thousands of millions of organic compounds. How do we now start classifying them? How do we now start identifying them? This is a very big problem. So what we did was to group them family by family. Now, this grouping will help us understand them. For instance, if you come to a particular city, you see a lot of people moving around, a lot of people running around. How do you identify each person? It's the family system. So there are families. So for instance, you want to share something. If you group them family by family, it will be easier to do. So this is the entire framework of what homologous series is trying to explain. Now, according to this definition, actually I got this from Ababio New School Chemistry. Homologous series is a family of organic compounds which follows a regular structural pattern in which each successive member differ from the next in molecular formula by CH2 or 14 grams. Now, I'm going to be breaking down these keywords: family, regular structural pattern, successive member, CH2. So these are the key things I'm going to break down. Okay, so we've gotten an overview of what homologous series is. It's simply dividing all the organic compounds, or rather grouping all the organic compounds into families. So some examiners can call it homolog. Some examiners call it homolog. So there are a lot of families, so many families. As you can see here, alkane is a family. Because some of you may have been wondering, I hear alkane today, tomorrow I hear alkyne, alkanol. These are all families. These are family names. So alkene is a family, alkyne, haloalkane, alcohol, ether, aldehyde, ketone, carboxylic acid, ester, amide, and so on. So now we've dealt with this word meaning family. So let's look at this regular structural pattern, because remember we said which follows a regular structural pattern. In which each successive member. So we're going to look at regular structural pattern and each successive member. So in every family there are members of the family. So you want to count, you start from father, mother, firstborn, secondborn, thirdborn, fourthborn. You get. So each of these families, they have their own firstborn, secondborn. So let me quickly go here. Now in organic chemistry, I have listed, whenever you see one carbon atom, the name must start with meth. Whenever you see two carbon atom, or rather C2, the name must start with eth. Okay, let me use another. So whenever you see three carbon atoms, C3 is prop, C4 but, C5 pent, C6 hex, hept, oct, non-dec, and so on. So what will now end this name of mate 8 probe will now be dependent on the family the compound is in. So for instance, we have alkanes, changing to red. We have alkenes, we have alkenes, we have alkynes. Okay, we have alkanol, which yeah, so these are all families. Now each of these families, they have members. For instance, the first member of alkane means carbon 1. That is, the first member must have carbon 1, and the first member is actually CH4. Second member C2H6. Third member C3H8. Or you'll work that down later. So how do we now name? We'll look at this family of alkanes. Whenever you see the family of alkanes, their name will always end in "-ins". For alkenes, their name will always end in "-ins". For alkynes, their names will always end in "-ines". So when we take the first few members, maybe the first three, we'll look at this carbon 1. So we call it propane. The second one, we call it not propane. Let me clean that. Forgive me for that. It's not propane. The first one, what's wrong with my marker? CH4. So this first one, CH4, is called methane. We are looking at one carbon atom. Methane. So remember, this is still alkane. Alkynes. So now the first member is methane. Second member C2H6 ethane. The next member C3H8 prop, because 3 is prop, so that's why I'm using propane. You can see that all of them have the same surname, N. If it were to be this family, it would be different. So if it were to be the alkene family, what we're going to have here, actually, it's good I make this very important point here, that remember, there is no carbon 1 for alkenes and alkynes. I will always tell my students this, that just assume that there was miscarriage here. You get. So when you assume that, know that there is no carbon 1 for this. Hence, there is nothing like methane. No. There is nothing like methane. No. However, from the second born, which is ethene, is correct. Ethane is correct. So for ethene, remember, it already told you there must be 2 carbon atoms. So C2H4. I am going to tell you how I derive this. Okay. For this, C2H2. So you can drive this down with the formula I'm going to give you now. Actually, we still have alkanol as a family, so I'm going to list all the families for you. So now, each of these families have what we call molecular formula to get all the members. So if you cannot memorize them, there is a formula for all of them. Every family, there must be a formula to derive all the members. So I'll quickly go back there. Okay, take this off. Okay, so I'm here right now, and now if you look at alkanes, you can see that this is their formula. So this formula, CnH2n plus 2. Using this formula, you can get all their members. So it is CnH2n plus 2. Going back here, so CnH2n plus 2. How do I use this? Where C is equal to number of carbon. So, where N is equal to number of carbon. So, let us start. The first member, the number of carbon is 1, so we have C. There's no need writing 1 below here. So we have Hn. How many H do you need to put? 2 times N. Remember, N is the number of carbon, and the N we have here is just 1 N. So we have 2 times 1, 2. So we have H2. 2 plus 2, 4. This is how we got the first member. If you apply it to this second, to get 18, you can also have C2. Remember now your N will become 2. 2 times 2, 4. 4 plus 2, 8. So this is how you can go through it and get C3. This is 6. 2 times 2, 4. 4 plus 2 is 6. And then C3H8. So this is it. And now alkenes, their general molecular formula is CnH2n. Just multiply C by 2 and you're getting it. And that's why for alkene you have the first member, which is 18, C2H4, C3H6. Just multiply the C by 2, C4H8, and so on. For alkynes you have CnH2n minus 2. So you have C, there is no carbon 1. Remember I said the first member out, there is nothing like the first member. It's 18 and ethyne is where it starts, from carbon 2. So you can have C2. How do you approach your H? Because 2n here is 2, so you have 2 times 2, 4. 4 minus 2 is 2. So this is ethyne. How do you get propyne? Prop is 3, C3. So you have to multiply 3 by this, 3 by these 2 here. So 2 times 3 is 6. 6 minus 2 is 4, H4. So you can do this to get all of the rest. I hope this is clear. So we go back. What I'm going to do now is to enlist. We go back. So you can see for all of them, applying this formula, you can get all of these homologues, or what we call families of organic compounds. So now let me talk about this. Remember, successive member means, the next one, the one that follows the next, and then we're about. So why is it that each successive member differ from the next by CH2? How come? This is a typical objective question. How come? Now remember I said that for the alkanes, the first member of the alkane is CH4, followed by C2, H6, followed by C3, H8. Now, the difference between this and the one on top of it should be CH2. The difference between this one and this one on top of it should be CH2. The same goes for all the families. How did I get CH2? 2 C's here minus 1 C here, you're getting C. 6 hydrogen minus 4 hydrogen, you're getting 2. It is constant. Now, how did we come about 14 grams? By 14 grams, carbon is already 12, and then hydrogen. The atomic number of carbon is 12, and then mass is 12. Then hydrogen is already 1, but we have 2 here. So we are getting 1 times 2 is 2. 12 plus 2, this is equal to 14 grams. So this is the mass of the CH2. So in case the question doesn't come in form of this formula, it can come like this. I'm quickly going to show you how we distribute these things. Remember, methane is this CH. This is how we draw the structure. This is how we draw the structure. You can see, because we treated tetravalency of carbon, when we did that, I told you guys that this carbon you're seeing, it can attach to 4 different molecules. This is the tetravalency we are talking about, and this is the reason why catenation is possible. So you can see hydrogen coming, hydrogen, hydrogen, hydrogen. Carbon at every point in time can bond in 4 different sites, provided it is one bond. There are exceptions when there are double bonds. For instance, if you have this double bonded to O, you can only have 2 other possible outcomes. So know this, there are only 4 bonds. Bonds are these hyphens that can leave from carbon. So it is either it goes up, left, right, down, or when there is always a presence of oxygen that collects 2, remember to put just 2. Is this clear? So having done this, let's look at this. Let's look at this very fast. So you can see the alkenes. This is the formula. Their functional group is single bond. I'm going to do functional group in the next video. Double bond for alkenes. Alkynes are triple bond. So look at that later. So these are the structures. This is ethene. And then you look at all of. So very quickly we get to look at properties of homologous series, characteristics of homologous series. So properties, or what we call characteristics of each homologue, that is of each family. So I am going to clean this right now. Clean up so that I'll have enough space. So number one characteristic we're going to look at is general molecular formula. Now each of these family, they have the same general molecular formula. The general molecular formula is what I told you, like this. These are the formula. Each of them have the same. So the same formula you use to get the first member, you use it to get the second member, you use it to get the third. So I'm sorry, that was an unexpected call. Okay, so we've talked about general molecular formula. General molecular formula. So each family, they have the same general molecular formula. This one is for alkyne, this one is for alkene. For alkane is +2. So the next point there is difference between each successive homologues. Difference between members. So let's just have it like that. Of course, the difference between members is CH2. I've illustrated this. The next one is physical properties. Physical properties. Now the physical properties of the members change gradually as the number of carbon atoms increases. So as a number, you can see the number of carbon atom increasing down this trend this way. So the physical properties and properties like the boiling point, properties like the melting point, density. So as the carbon atom is increasing, they are increasing as well. So as carbon atom is moving from 1 to 2 to 3 to 4, the boiling point is. And this is why from carbon 1 to carbon 4 are gases. Don't forget this. From 5 to 17 are liquids. From 18 and above are waxy solids. So we're going to talk about the solubility as well. Their solubility in water. Now, as the number of carbon atom is increasing from 1 to 2 to 3 to 4, the solubility in water is decreasing. Solubility decreases as carbon atom increases. So you check this out. So this simply means that this is less soluble than this. This is less soluble than this. So carbon 4 is less soluble than 3. 3 is less soluble than 2, which means 2 is more soluble than 3. This is just it. So they have, the next one is chemical properties. Chemical properties. They have the same chemical properties. The next one is method of preparation. They have a general method of preparation. Method of prep. So they have the same method of preparation. So this I'll need to clean this up, or rather I would like to take you back. So this is just the highlight of. Okay, I'm going to take this off. So clean. So I just want to give you an overview of all these families once again. So we now understand. Okay. So we now understand that. Now here are all the families. We've talked about alkenes, alkynes. Now we have alkanols. These alkanols, some people call them alcohols. we have alkanoic acid, or carboxylic acid. We have aldehyde or alkanal. These are all different families. We have ketone or alkanone. We have ester. Yeah, this is the ones that they have very sweet fragrance. They are normally used in making flavors and perfumes. We have ether. We have haloalkane. These are all families, different families. Am I forgetting any one of them? Okay, so we have amides. We have amine. So this ester can also be called alkanoate. Now, how do we know them? For alkanols, whenever you see OH, now these are the functional groups. We're going to look at this in our next video. For now, I just want to establish all these families. So functional groups are things you see, and then you know that this is surely this family. So maybe this family, they have pointed nose. So whenever you see pointed nose, you're sure, this should be Johnson's family. You understand? So we're going to look at that. For alkanoic acid, you have COOH and the rest of them. So thank you for your time watching this video. I'll actually want you to hit on the like, subscribe, share, comment. Thank you, and see you next time.